Morning, everybody. Morning. Welcome, welcome. We have two very special guests here. Alejandro and Andrew are from the Tutorial Center, right? And they want to tell you how wonderful the Tutorial Center is. And you're going to put a plug in for GRASP, right? Okay, good. Go.
Good morning, guys. I'm Alejandro. That's Andrew over there. We're here on behalf of the Tutorial Center just to inform you guys of the tutoring services that you guys are going to receive. So if you're struggling in your physics class, your math class, science class, assembly, any class, history, English, you need help writing the paper, you can go to the Tutorial Center. It's room 138. If you don't know where the main library is at, and like the computer lab and the financial aid office are like right in between there. There's a giant sign you can walk in there. All you need is your student ID. You can walk in, you punch in your ID number, and they'll ask you for the class you're going to be tutoring for, and then they'll kind of get you situated on where you're where you'll sit. The pamphlet that Andrew passed out has a QR code. So unfortunately, we tutors are students just like you guys. So if you're looking for tutoring for a specific subject, a tutor may not be there. So that QR code has a list of all the tutor schedules. So you can go, let's say just physics 2B, you can go in there you can find a time for physics 2B and you can get tutoring for you. If in-person tutoring doesn't work for you, there's also a section on there for online tutoring. So you can do like a Zoom call. Yeah, a Zoom call. Over here. What else?
Alejandro, can I stop you for a second?
Yeah.
I know it says on Thursday, it says not available for Physics 2A and 2B all day. That's half true. There's no like dedicated 2A, 2B tutor, but I'm going to throw these two under the bus and say they can do 2A and 2B also.
Yeah.
Right? Okay, so the fact Physics 4 tutors can do it all,
Yeah.
right? So if you have a tutor that's scheduled for Physics 4B, they've got you covered,
Yeah.
right? So.
And like even if you're not struggling, it's a good place to go. There's whiteboards everywhere. It's a good place to make connections. You'll probably run into someone in the same class as you, and you guys will like form little study groups. Or if you're me, you'll go there and you'll end up working there. So yeah, go ahead and check it out. It's a good place. All the resources for you guys. Any questions?
The hours are also 8 to 7 Monday to Thursday, and then 2 to 7 on Friday, and 2 to 7 Sunday.
So
8 to
Monday through Thursday, it's 8 till 7.
Yep.
Yeah.
Fridays it's 8 till 2, I
Yeah.
believe.
Mhm.
You guys have physics graphs on Fridays as well.
Over here, yeah.
It's 8 to 1 on paper, but I think Balogh opens up an hour earlier.
7,
still.
yeah, I'm there at
So you
7.
guys- It's 7 1, so I'm sure you guys know that. But yeah, a lot of resources for you guys available.
I highly recommend physics graphs because it's not just tutors; it's also professors that can answer
Yeah.
your questions.
Yeah.
So I know sometimes it feels weird asking another student for help
Yeah.
because I was there, but professors are there.
Yeah. Yeah. There's a lot of options.
Tutors know more than we do. We can fix Wiley Plus. It's the only advantage we have over the tutors. The Saturday is not in session, right? No Saturday because students need day off too.
Yeah.
Yeah, Sundays we're there 8 till 2.
Right.
Yeah.
Right.
All right.
That's it.
Thank you guys.
You going to be in GRASP this semester?
No, not this semester.
What did we do to you? Was it that bad?
It wasn't bad. It's just-
Should I walk away?
Get out, Andrew. While you still get. Everybody, give them a hand. I mean, they get paid, but our tutors are great. We really enjoy having them. So thank you. Yeah, and it's always good to hear it from fellow students, right? And not just from your physics teacher who doesn't know anything. I'm too old to be believed anymore. So. Yeah. Your generation doesn't pay attention to mine. So.
You start getting gray hair.
Yeah, right. Okay. We need to finish chapter 20 today. Oh my gosh. I published the topics list this morning. I don't know if you saw that announcement. I did it for my 2A students as well, but I think more than half of them missed that. But that's their problem. So the topics list has been posted. For those of you that didn't have me last semester, I just put down like all 7 questions, what the topics are. Mm-hmm. And they're just in alphabetical order. When I print them out, the computer randomizes the order of the questions. But you have all 7 topics for the 7 questions that will be on the exam, right? And if you look on there, you'll see one is conceptual in nature. We're going to talk more about the exam on Tuesday as part of the review. On Tuesday, make sure you're coming with questions for me, right? Because I'm not going to present any new information. I'm not going to ask you more questions. Students sometimes ask me, Mr. Balogh, do you have like a preview test or a practice exam? And my answer is yes, it's called homework. right? So that's kind of what I do. There is a link to like a sample exam on the Canvas site for my classes. It'll say Physics 2A all over it, and it is. It's like 2A problems and stuff. It's not meant to like show you what's coming up for this exam. It's just meant to show you like the two kinds of questions you'll encounter: the conceptual question and then the other type, which is like a mathematical, analytical type question. So if you haven't had me before, jump there. It's in the Unit 1 down at the very bottom, underneath the Chapter 20 homework stuff, and you'll see a link right there for it. It's also a link in the announcement. Let's see. And then next Thursday we're taking the exam, and after that we're getting into magnetism. So let's conquer this. So schematic circuit diagrams, right? We're going to be in the thick of it now. And I already gave you some of the symbols that we use when we kind of lay out or map out circuits. So let's talk about the two ways that you can connect stuff together. We're going to do this in the context of resistors. And for our purposes, a resistor is anything that uses electrical energy. It could be a true physical resistor. It could be a light bulb. It could be a cell phone. It could be a microwave, a refrigerator. It doesn't matter. In physics, we tend to say, you know what? The refrigerator takes up energy. It's acting like a resistor. And it's a good lie. Like if you really want to map out what's going in your house, just assume everything's a resistor and you're going to get the right power and all that kind of stuff. All right, so series and parallel. The name series suggests what? How would you connect resistors in series? One after the other, right? Now, that can take a lot of different forms. Don't write down all these pictures because I'm going to erase most of them, okay? But for a series connection to take place, so here's one resistor, right? I have to connect the next resistor one after the other, right? Now, where I do that doesn't really matter, okay? Like I drew those 4 resistors like that. I could have drawn them like this, right? Those 2 examples are exactly the same, even though it's rotated and is equivalent to that. So how do you know when resistors are in series? What are you looking for?
One after the other?
There can be no junction, no splitting of a wire between the elements. I like to think of it as like you're walking along as a charge along this thing, and if you want to get from one end of the wire to the other, you have to pass through the resistor. That's series. Okay? So let's compare and contrast then with parallel. I lied. I said I was going to erase. I'm not going to do it. I'm just going to get a new, you know what I'm going to do right now? And we'll bring it up later. Okay, so parallel. What would that look like? This is what a parallel set of resistors might look like. That's a very common way of drawing parallel resistors. They're sort of all like kind of lined up with each other, right? Okay, even parallel to each other. But actually, they don't need to be drawn parallel to each other. This is exactly the same circuit. Did your brain just go boom? Actually, it's not the same circuit. I lied. This wire is screwing everything up. Here, we'll do... Mr. Bailey needs to be more careful about his diagrams. There we go. This one is the same. Okay? So it's not necessarily where the resistor is drawn. It's where it's drawn in relation to the junctions that always exist when you have a parallel connection. Notice, as we come along this wire, we get to a point right here where a charge has to decide. And what does it have to decide? Which path is it going to take? A charge cannot take both paths. It can only take one. So a charge is going to go this way, or it's going to go that way. So a junction means that the wire is splitting, right? There's more than one direction. You can have 3, 4, 7, 10-way junctions, right? But the point is that you have a charge moving along a wire, and it's got to take one of many paths that it could take. That's different than series. Charge comes in here, has to go through this resistor. Does it have a choice? No, it has to go through this next resistor, so on and so forth, through the different combinations. And of course, you can do things like this. Right? You can have mixed circuits, okay? So is there anything that's sort of like obvious to you about what's in parallel and what's in series in that black diagram? What do you think? Let's look at that one. Is it in parallel or series?
Aren't they technically all in series because that first one is before any of the junctions?
Nope. What's it in parallel with? I mean, how did you know this is in parallel?
Because it's after a junction.
There's a junction here and there's a junction there, right? Okay? And it's in between those junctions. So this has to be in parallel. But what is it in parallel with?
Those other three.
Is it in parallel with this one?
Yeah.
What about this one?
Yeah.
Simultaneously?
Yeah. Because they're in series with each other.
But these two are in series with each other. So how can this one be in parallel with that one while simultaneously being? Do you see where the problem is starting to begin? Are these obviously in series?
Yes.
Why?
There's no junction between them.
They are connected one after the other. So these are in series with each other. Okay. What about these two over here?
Those are in series.
Why are they in series? Because there's no junction. This corner is not a junction, right? It's just a corner. Schematic diagrams tend to be drawn in like a block format. They're sort of aligned to a grid. I mean, technically, I can draw this like however I want, right? Okay, but we don't do that because it isn't clear, right? We're trying to sort of clearly indicate what's in series and what's in parallel. In fact, I would probably like redraw this outer branch to be this, right? If I was the one drawing the picture, just to be clear that those two are in series and they form a parallel branch with everything else. So what we need to do is we need to develop a skill where we can instantly identify things that are in series, okay? Separate that out from things that are more difficultly maybe be in parallel, like this is parallel simultaneous and this is parallel simultaneous. It can get really, really involved really fast. So what I'm going to teach you is a systematic way to work through all of these connections. And the way we're going to do it is we are going to combine resistors together theoretically so that ideally we can take this whole circuit and boil it down to a single battery and a single resistor. Even if it's a bunch of things connected, as far as the battery is concerned, it just has to push a certain amount of voltage, right? It doesn't really know what all the individual things are. But we can do a lot of circuit analysis if we can do that. So let's formalize. That's sort of the overall idea, right? Okay. So I'm just going to draw a series of, I don't know, 3 resistors here, R1, R2, R3. They can have as many connections as we want. To be in series or parallel really needs to be in reference to a battery of some kind, a connection. Sometimes you'll see problems where they won't indicate the battery. They'll be like these pictures over here. Do you see how I didn't draw any like batteries on these? And they'll just say, between, and they'll usually label the points, right? But they'll say between these 2 points, Are they in series or are they in parallel, right? And what you got to do is you just kind of have to imagine there's a connection here, like a battery, okay? So series and parallel almost always is in reference to the voltage source in the circuit, okay? So I've drawn 3 resistors in series with a battery here, and I don't want to fill your brain with how we come up with some of these things. I'm just going to tell you what the equations are and then show you how to utilize them, okay? So we can figure out what the total resistance of this setup is by simply adding together all of the resistances. And if I put plus dot, 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 what does that mean? Keep going, right? So if you had 4 resistors in series, what would you do?
Add a fourth.
Just add it, right? Okay. So any resistors in series, you just add their resistances together, and in so doing, you end up with a equivalent or overall resistance that is always going to be higher than any of the resistors that went in. So if you want to increase the resistance of any electrical setup, what do? How do you connect things?
In series.
In series. Series is always the way to get things to be as big of a resistance as possible. All right. You want to take a big guess as to what happens when we connect things in parallel? No, that's a good guess, but it's wrong. Does the resistance go up or down? No, it goes down. If series makes it get bigger, right? The overall resistance of the circuit is bigger. In parallel, it's smaller. And the way we write that is the inverse of the equivalent resistance. 1 over the equivalent resistance is equal to the sum of all the inverses of everything that went into it. Okay? So these are the mathematical rules. They are derived from physical law. I want you to know that I'm hiding from you because you really don't want to fill your brain with that stuff. Okay? But these equations in the boxes are reflections or expressions of the energy and voltage and charge of what they're doing in these connections. Okay. Along with these mathematical statements, there are some conceptual ideas we have to hold on to make sure that we can do circuit analysis correctly. This is a little bit awkward. This is how I do it. I've seen kind of different books try to express the same idea different ways, but this is what I do, okay? Whatever the current coming out of the battery is, that current is identical when things are connected in series. There's no choice, really. If 10 amps of current are coming out of that battery, all 10 amps flows through resistor 1. And then where does it go? Through resistor 2, right? Current, it needs to make a loop. Like the battery is what pushes the charges around, and so those charges leave the battery, and to get back to the battery, they have no choice. They have to go through all 3 of the resistors in that circuit. And if there were 5 resistors in series, that current has to flow through all 5 resistors. So when resistors are put together in series, the current through them is exactly the same for all resistors. That's conservation of charge is what that rule is right there. The voltage, this is going to be a conservation of energy statement. The voltage that the battery puts out, I don't know, let's say it's a 12-volt battery, okay? The voltage put out by the battery turns out to be the sum of the voltages that are in the individual resistors. So these resistors probably are not all the same. If they were all identical, this would be easy, right? It's 12 volts split up across 3 identical resistors, so what voltage is on each resistor? 4, right? 4 plus 4 plus 4 is 12. That's conservation of energy, conservation of electric potential, okay? But if the first resistor took 6 volts and the second resistor took 3 volts, then how much voltage would be on the third one? 3. We've always got to add. That's what that statement right there says. Whatever the voltage in the battery is, right? That I like to think of it as being shared. I say that the current's the same, meaning it's equal, identical, but the voltage is split or shared across all the elements in series. Yeah, unfortunately. Okay. So in the red box, we have the mathematical statement for equivalent resistance. But in the blue box, we have the very important conceptual ideas of conservation of charge and conservation of energy expressed in terms of electrical ideas, current and voltage. So in parallel, whatever voltage comes out of the battery is the voltage in each of the resistors. All 3 of those resistors are going to have exactly the same voltage. And if you look at like this side of the battery, right? Okay, this is the positive side. All of these resistors have connections to the positive side of the battery. And so if this is a 10 volt battery, this entire rail right here has to be at 10 volts. And so each resistor, right, also has a connection to the negative side of the battery. So the potential difference across the battery is 10 volts. That means the potential difference across every resistor has to be identical, because all the resistors are connected simultaneously to the positive side of the battery and also the negative side of the battery. So the voltage is the same. It's equal when you connect resistors in parallel. When you connect resistors in parallel, the current is the thing that gets split up or shared. So if 10 amps is coming out of that battery, okay, and 2 amps flows through the first resistor, how many amps are now right here? So 10 came out, 2 went this way. So in this wire right here, how many amps are there? What's 10 minus 2? 8. There's only 8 left over. At this junction, the current has to split. And if 2 goes this way, 8 went that way. And now at the next junction, if 6 comes along here, then how much is right here? 2. Okay? This is conservation of charge, but it's for this situation where we're splitting up these charges as they go. Okay, so those are, this is like the cheat sheet for series and parallel resistors, right? If we've got the rules for how to combine resistors into theoretical, just one big resistor, and then we have these rules that give us the statements of how things are conserved in the circuit, we can figure out any circuit that exists. The good news for you is they're not going to be too complicated, okay? Because like circuits can get really bad really fast. But let me ask you this as sort of an application of what we're talking about here. Let's just think about your kitchen, okay? Wherever you make or cook food. Your microwave, your refrigerator, your stove, the coffee maker, whatever you got plugged in, the blender, are they connected in series or in parallel in your house? Parallel? How do you know they're connected in parallel?
Outlet is the junction, right?
Are they?
Well, so the power isn't going through one device and then going to the next.
How do you know that?
Is it not?
I'm asking, how do you know
I
that?
don't know.
But you are a physics student.
One guy doesn't know.
Right. In series, if I unplug this resistor, which could be the microwave, okay, then what happens to the path of flow? It gets cut, doesn't it? Okay, yeah. Okay, in series, if I were to just break this resistor and pull it out, I would have an open circuit and no current would flow. Okay? That's how you know that your house is wired mostly in parallel. You can run the microwave independent. Wouldn't it suck if your refrigerator only worked if the microwave was running? Right? Or you woke up in the morning and you had to plug in the coffee maker and the microwave and the refrigerator before the stove turned on. Right? Okay? That's what would happen if it was in series. You'd have to have everything connected. But that's not how it is, right? You can plug things in independent of each other because in parallel, if I don't have that one connected, are the other two resistors still connected to the battery? Yeah, right? They have independent paths to get to the battery. So you're like, well, why would anybody wire anything in series? Well, I already gave you one clue. If you wire things in series, what happens to the resistance? If you need lots of resistance, you'd want to wire in series. But there's another part of your house that is wired in series. And it's very important that it's wired in series. The bathroom. That's a good guess because a lot of times the bathroom is the cause of a problem. Okay? How many of you have the little outlet in your bathroom that's got the two little switches in it, right? And they pop at a moment's notice. It's like a hair trigger, which is good because they're designed to detect faults in various things, right? And then that turns off the entire, all the bathrooms or the entire floor or whatever, right? There are safety devices that are hooked up in series. The breakers are all hooked up in series with whatever branch it happens to be on, okay? And you want it to be in series because if you plug yourself in and you're drawing a lot of current, in other words, being electrocuted, you want something in series to switch off, right? To kill all of the current in that branch, okay? So breakers and the GCFI outlets that always look to see if there's a little bit of energy leaking to ground, which could indicate a problem, they will trip off and kill a bunch of things because they're wired in series with that circuit. But the individual plugs in your kitchen and stuff, they're all in parallel with each other. It's a little bit of a lie. Usually the microwave has its own circuit. And there's a bunch of code stuff, but in general, most of your house is wired in parallel, and then there are certain things, the circuit breakers, that are put in series. Car wiring is kind of interesting. Lots of combinations of series and parallel in a car. You can always tell when a car is wired in series, like if one headlight goes out, they all go out. That's kind of an older way of doing it. Nowadays, they kind of wire everything in parallel with lights so that if one light goes out, the rest stay on so that you get a fix-it ticket because you didn't realize that your headlight was out. Ask me how I know. There's just different systems, right, that are worried depending on what they're trying to do in the vehicle. All right, let's just help you conceptually sort of see what's going on. Here's another way that you can conceive of series and parallel resistors. Did I? I didn't. I had almost all of the buttons pressed. So many buttons.
The resistance of an electric resistor is proportional to its length inversely proportional to its area and proportional to its resistivity.
We did this last time, right?
To inhibit the flow of electrons. This tendency to resist is something all materials have, but to varying degrees. Adding resistors to a circuit, one after another, has the same effect as making one resistor longer. These are called resistors in series. Putting resistors side by side increases the area through which the current can flow. These are called resistors in parallel and they have a lower resistance than either one alone.
So I was arguing earlier from just conservation of charge to conservation of energy, but this goes back to what we learned about resistance last time, about length and area, right? Series causing the length, effective length of a resistor to become longer, and parallel causing the effective cross-sectional area to become bigger. So again, just sort of another way of thinking about this series and parallel combination. Oh, quiz coming up. Forgot about that. Wait, hold on a second. What quiz is this? We're going to skip this quiz. What? It's kind of a dumb quiz anyway. Okay? Yeah. It's like light bulbs in series and in parallel. There's more things going on with the light bulb than you need to worry about. Okay, so let's do, sorry, that was a psych. Let's do, all right, so what I want to do is I want to walk you through circuit analysis. This is the process by which if you're given a circuit, you can find out everything there is to know about every single device in this circuit. I want to preface this with, I know you're going into careers where you'll never have to do this again, hopefully. Okay? Because this is bad. What we're about to do is bad. Okay? However, various professional organizations and exams like the MCAT and other things, they want you to have the analytical skill that I'm about to display, right? Because this type of analysis, this algorithmic step-by-step way of going through things is replicated in a lot of different places. So yes, in this class you have to do it in terms of like circuits, but try to learn the process and sort of like the tips and tricks I'm going to teach you to keep information organized. Because what we're about to do, I think, is difficult, but none of the math, like the actual mathematics of what we're going to do, is going to be very hard. If you can add and divide, you're good. Okay? That's it. It's going to be divide one thing by another, add one thing to another, and we're done, right? So the actual math is not difficult. What is difficult is the application of these rules that we talked about to these circuits, and most importantly, most difficultly, keeping track of all the information, because there's going to be a lot of things to keep track of. And so if there's one thing in my career that is as close as you can get to accounting, this is it. Okay? Accounting, by definition, is doing second grade math a lot. Right? And so it's keeping track of all that second grade math that is going to be the difficult part. So accept this, let it wash over you, let it flow. Or just panic. Either way, it's all good. Let's see. Let's start with a 15-volt battery. So here's my battery symbol, 15 volts, okay? And I'm going to, for the sake of this example, I'm going to do something silly. I'm going to label all of the resistors, 1, 2, 3, 4, 5. There's going to be 5 resistors in this circuit, okay? And then I'm going to set the resistance equal to its label. Oh. So R1 is going to be how many ohms? 1 ohm. R5? 5 ohms. The only reason I'm doing that is to help us keep track, right? In reality, the resistors could all be the same. They could all be different. You'd have to know the values. But the process will stay the same. And to keep this process as clear as possible, I'm just going to, because I'm a physicist and nothing's real that I do, I'm going to go ahead and just make the resistances be what I label them as. This one's going to be R5 because R2, D2, and R3 are right there. And then I'm going to put R4 like that. That's the circuit. This circuit, I don't know what it is. It could be the wiring diagram for your bottom floor of your house. It could be the kitchen. I don't know what it is. I don't care. Okay? But our goal, our stated purpose for circuit analysis is to find out everything there is to know about every single resistor in this circuit. So let's take a step back. What could we know about all these resistors? You might want to meditate on it. Ohm's law. Okay, we have a battery that has voltage, right? So Ohm's law, V equals IR, is going to be there's your toolbox, right? Like that and the other screen that I had, right? That's basically the toolbox. But if we know the resistance, then we could know the voltage and the current through every single resistor in this circuit. Knowing the current and the voltage, we could also find the power. These are all things that we've been talking about up to this moment, right? We've just been prepared for this moment. So what I do, so what we're going to do is we're going to find out everything. We're going to find the voltage and current and power through every single resistor in this circuit. Oh, let me also say that I'm going to stand over here because I shouldn't say things like this. This is my zone of me admitting something. I hate circuits. Like, that is the proper word, okay? It's not hyperbolic. I truly loathe and despise circuits, okay? The feeling is mutual, okay? I hate it. It hates me, okay? And for proof, I present this story. In college, physicists have to take a circuits class, okay? And in that class, we do all this analysis, we do some pretty hairy stuff, but we also have to build physical circuits in the lab, okay? One of the jokes about circuits is that if you do something wrong, you short something out, you burn something out. When you burn out a resistor or you explode a capacitor or do anything like that, smoke comes out of your circuit board. And so the joke is that if you let the smoke out, the circuit stops working. Right? It's the smoke that makes the circuit work. And if you let it out, this is just something we do to keep sanity in circuits lab, right? There is an element in a circuit called a potentiometer. It's a variable resistor. And anytime you grabbed a dial anywhere in your car, you've probably grabbed a potentiometer. You twist it and it changes something, like how hot and cold the thing is, or frequency on the radio or whatever, right? Nobody listens to radio anymore. But potentiometers exist all over the place. Because potentiometer is a word that takes too long to say, human beings will shorten it. And in circuit theory, you shorten it to pot, P-O-T. And there's 3 connections on a potentiometer. And no matter how many times I was told, no matter how well they were labeled, no matter how consistent I was at soldering these pieces together, I always managed to blow up my potentiometers. Always. And smoke would come out and all that kind of stuff. Okay? So the joke became, okay? So context for this joke. You have to realize I went to Brigham Young University, which is a religious university. There was a strict honor code and health code. So no drinking, no smoking, anything on campus. And so the joke became, Balogh's here, he's going to be smoking pot in circuits lab. Because anytime I was in there, people could just walk in and go, oh yeah, Balogh's here, right? I hate this stuff. I really do. But nonetheless, it can be conquered. Okay, this is what I do. I make a table. I make a spreadsheet. Because spreadsheets are the way that accountants organize things. So, hey, let's take a page out of their book. What does my spreadsheet look like? Okay, it looks like RVIP. I really wanted to do RIP as in rested, but I couldn't do it. RV, give a little bit of room. IP. Okay, so what this little table is going to do for me, you don't have to do it this way. If you find a different way that works for your brain, fantastic. Okay, but my brain tends to work in spreadsheets. So I've got resistance 1, 2, 3, 4, 5, and that's in ohms, right? Okay. And then I have a column for voltage, and a column for current, and a column for power. Any time in the subsequent process that I actually learn something like the actual voltage of resistor 3, I'm going to put it in my table. There's going to be a lot of calculations. There's going to be a lot of pictures. Again, keeping track of what we're doing, vitally important. Okay, what we want to do, where you start, okay, after you get sort of the picture set up and your table ready, what we want to end with is a picture that looks like that. That's the ideal circuit, right there. It's the simplest circuit in the universe, a battery connected to a resistor. But this resistor down here is going to be the equivalent resistor of all of these put together. But do you see the struggle that we're going to have to go through?
That's REQ.
Yeah, this is like REQ down here, okay? The equivalent resistance. We have to figure out how to combine all of these resistors together into one resistor, keeping track along the entire way of what we did, because we're going to have to work backwards. So what we are going to do is we're going to do some circuit origami. We're going to do a bunch of folds, and we're going to get this thing down to whatever shape we want it, and then once we get there, we're going to unfold it to see where all the creases were. Too many analogies, Mr. Baylor. Just do the problem. Okay, fine. Right? I'm trying to prepare your brains for what's about to come. Where do you start with this? You can start really anywhere, but my advice to you as a new learner of this process, start as far away from the battery as possible. The resistors here and here, are they in series or parallel with each other?
Series. Well, no, there's a junction.
There's a junction right there, right? But you can't just add them together and have the same circuit exist. Like if you put these two in series, you basically cut off all of these parts, okay? Since R1 and R5 are close to the battery, ignore them for now. We'll take care of them later. We want to get as far away from the battery as we can in this circuit. So that's 2, 3, and 4 right here, right? Okay? And we want to ask ourselves the question, are there any obvious connections? Things that are just like immediately jumping out at you that are totally obvious whether they're in series or in parallel. R2 and R3, what are they doing? Why are they definitely in parallel? They're literally, I drew them in parallel. But there's junctions. Do you see the junction before and after? There's a junction right here, and there's a junction right there. So current, whatever it does, will split up at this first junction, and then it splits again, doesn't it? And then those come back together on the other side. So I can look here and here and go, junctions on either side, these two must be in parallel with each other. So that's what we're going to do first. We're not going to touch any other part of the circuit. We're going to leave the rest of the circuit alone. We're going to redraw. There's R1. There's R5. We'll get them labeled, okay? And then we're going to draw just another resistor that represents the combination of 2 and 3. And I'm going to call it R23 in my label. Again, you're going to have to come up with some other way to keep track of these things, right? But this R23 resistor is the combination of 2 and 3 together. We said that they were in parallel, right? So how do we add resistors in parallel? Parallel side, equivalent, 1 over equals 1 over plus 1 over plus 1 over. So this is what we have to do. Oops. Not something you want to hear your teacher say when they're lecturing. Okay. We need to do, and I very cleverly left no room to do this calculation in, so we'll just move that down because electrons. 1 over R23, because that's what my combined equivalent resistor is going to be, right? Is going to be 1 over 2 plus 1 over 3. Remember, I'm doing this, I'm being cute, right? So if your R2 and R3 were like 20 and 30 ohms, you'd have to put 20 and 30 in, right? Okay. So how do I solve for R23 here? Like sort of mathematically.
You just add a half and a third.
I do 1/2 plus 1/3. I have no idea what that is.
And then inverse it.
It's, let's see, that's 3/6 over 2/6, so it's 5/6. You know, I suggest you don't do it that way. I suggest you just put it in your calculator, okay? But is the answer 5/6? Is R23 equal to 5/6? No. 1 over R23 is equal to 5/6. So what's the last thing I have to do to get R23? I have to invert 5/6 to make it 6/5, which is 1.2. Where'd my black one go? Nope. All right, you get blue today. 1 over 2 plus 1 over 2 inverted.
What?
1. What's a half plus a half?
1.
1. What's 1 over 1?
1.
Okay. 1/4 over 1/4. So what's 1/4 plus 1/4? It's a half, and then you invert it, becomes 2. Do you see what's going on here?
Doubling the bottom.
Okay. Well, no, it's not just that. Like, one of the key mistakes that people make is they're fine with doing like the 1 over plus 1 over plus 1 over in their calculator, and then they get a number, and what do they then forget to do? Invert that. Okay. It's really important that you remember to invert your final answer. On your calculator, there's a button. It either looks like 1 over x or maybe x to the minus 1.
1 over box.
Okay. 1 over box.
That's how it is on the TI's 36
I hate TI. Okay. Right? So there's something along this theme somewhere on your calculator, if your calculator has a lot of buttons. Okay. You can put in the number. Okay. You can put it like for this one, you would do 4, and then you'd hit that button, and it would spit out 0.25. It's just the inverse button, right? Okay. So there's ways to like, once you get your thing done and you want to invert a number, you can just hit one button, or you can do 1 divided by ANS, which is the way, is that how TI does it, right? And you can get it done. Just don't forget that in parallel, yes, you're adding the inverses, but the very last thing you have to do is invert that answer. It's over here, it's stated right in that equation, right here. It's 1 over REQ. And if you want REQ, you have to invert at the end to get it. Okay. Whoa! That was only the first step. Okay. Now that we're at this situation, we're going to look at this new circuit we've got. It's not a real circuit anymore. It doesn't consist of purely physical resistors, right? But it is a theoretical, we brought things together, right? Okay. Start again, as far away from the battery as possible. Is there anything that's like jumping out at you that looks obvious, whether it's in series or in parallel?
2, 3, and R4. And parallel.
R2, 3, and 4 are in parallel? No, they're not.
No, there's no junction.
There's no junction. I can go from R2, 3, continue along and pass through R4 without ever splitting the wire. So they're in series, right? And so what is the next picture going to look like? We got the battery. We haven't messed with R1. We haven't messed with, we haven't been able to draw. We haven't messed with R5. But what will this new combination look like?
Another path coming off.
Okay. I could draw it like this, or like this, or like that. Those are all the same. They're identical. I'm going to draw it like this. Okay? So what is this? This is R2, 3, 4. And how did we get R2, 3, 4?
Just adding R2, 3, and R4.
Yeah, we're combining these. Boy, my drawing's going to get really messy here quickly, right? And by putting those together, right, R2, 3, 4, since 2, 3 and resistor 4 are in series with each other, what do we do? We just add them together. That's all we do. What's 1.2 plus 4? 5.2. Okay. We take another step. Again, we work as far away from the battery as possible. Is there anything that jumps out as to whether it's in series or in parallel?
R5 and R2.
These two right here, what are they?
Parallel.
How do you know?
Junctions.
There's junctions right there. Okay. How are you going to get good at identifying series and parallel? Practice. You're going to look at like every problem at the end of the chapter, and you're not going to read the problems. You're just going to look at the pictures. You're going to look at the picture, and you're going to quiz each other on, okay, which of these are in series, which of them are in parallel. And you're just going to you're going to fail, you're going to fail, you're going to practice, you're going to fail, you're going to practice, right? When I tried this last semester with any of the AIs, it was a dumpster fire. It was an absolute dumpster fire because how good are AIs at generating circuit diagrams? They hallucinate like crazy. You think they had trouble with like number of fingers on humans way back when?
How many S's or R's are in strawberry?
Yeah, but like don't ask ChatGPT to, hey, can you give me some practice with series and parallel and draw me some diagrams? It's on drugs. Like
Bayless with a
no, like mushrooms. Okay, like yeah, it's bad. Okay, so these are in parallel. Oh, come back here. Why did it not pick up my green? There we go. So these are in parallel right here. So how are we going to add them together?
1 over.
So 1 over R2, 3, 4, 5 is going to be 1 over R2, 3, 4 plus 1 over R5, right? So this is going to be equal to 1 over 5.2 plus 1 over 5. So what I'm going to do is I'm going to cheat a little bit with my pen. R2, 2, 3, 4, 5 is going to be the inverse of whatever's inside there, right? Whatever I do to one side, I do to the other. And then when I did this, I got 2.55. Okay, so what are we left with now? Going down here. We have a battery. That's wrong. We have R1. And then I just have R2, 3, 4, 5. At that point, you could probably just call it R2.55, right? Come up with ways to keep track of things in your diagrams. So now what do I do here at the very end?
They're in series. So you
Yeah. Oops. These are all in series. What I've tried to do here is use blue whenever I had a series connection and green whenever I had a parallel connection. I think I did it. I think. So let's see. The R equivalent is going to be R1 plus R2, 3, 4, 5, or in other words, 1 plus 2.55, or an overall equivalent resistance of 3.55 ohms. Now, on some of your homework problems, all they're going to do is ask you to find the equivalent resistance of the circuit, right? So if that's all they've asked you to do, you're done, right? You found the equivalent resistance, put it in the box. When it turns red, cry a lot because having to go back and figure out where you made the mistake, it's going to take a while, okay? But we're not done. We're only halfway done. I said I wanted to find out everything there was to know about everything in this circuit, right? What have we found out so far?
REQ.
We know what the total resistance that the battery is connected to, right? The battery doesn't know about all the series and parallel stuff. All it knows is that it's connected to 3.55 ohms of resistance. So if the battery is, what did I say, 15 volt battery, and it's connected to a 3.55 ohm resistor, what's the third thing we can find? Current, because of Ohm's law. So far we have applied the series and parallel addition rules, right, for the resistors. Now what we're going to do is we're going to apply Ohm's law going backwards. We're going to go back through every step. Remember I said we're going to unfold the origami and look at all the folds? We're going to go backwards through our entire circuit. We're going to start down here. We're going to go up and over and through and come back. And at every point, we're going to say, did we do series? Did we do parallel? What's the rule? And what does Ohm's law tell us? So down here, Ohm's law tells us that we can get the total current because we know the total voltage coming out of the battery and the equivalent resistance of the circuit. Did I do that right? I did. Okay, so that's 15 volts divided by 3.55 ohms. Can't read my writing. Where's my current? I solved for voltage. I solved for everything except the current. Is it 4.23 amps? Okay. Can't read my own writing. 4.23 amps. I made it nice and small down in the corner because it's such an important number. Now what I did is I ran out of room. Okay. So we now know the total current that is coming out of this battery. So let's work backwards. Where did this resistance come from? Well, the equivalent resistance came from the combination of R1 and R2, 3, 4, 5. What do we know about that combination? Series or parallel? Series, because it's blue, right? Okay. What is the rule for series combination when it comes to current and voltage? What's the same? What's split up?
Current is the same in voltages.
Current is identical, right? If current is identical, if 4.23 amps of current comes out of this battery and these two things are connected in series, what must be the current through R1? 4.23. R1 is an actual physical real resistor, so I'm going to write that down. 4.23. By the way, this is in units of amps, volts, and watts. Okay, so I found out a piece of information, so it goes in my spreadsheet, goes in my table. Okay? But we also now know what the current is in R2345, right? It's 4.23 amps. We know that this is a 2.55 ohm resistor, right? R2345, right? We found R2345 was 2.55 ohms. If we know the current and the resistance, what can we find? The voltage. So let's find it. Remember I said we were going to find everything? Current, resistance, voltage is going to be Ohm's law. So this voltage is good. So the voltage through 2, 3, 4, 5 is going to be 4.23 amps times 2.55 ohms. 4.2, is that 10.8-ish? Okay. Where did V2345, where did that resistor come from? R2345, what was it the combination of?
R234 and R5.
R5 being a real resistor, right? And 234 being a equivalent or theoretical resistor. How are 234 and R5, how are they connected to each other? In parallel. I did a green box for parallel, right? Back to our rules. What is the same? What's identical in parallel? Voltage. Do we know the voltage for this parallel combination? Yes, we do. Why did I do amps down there? 10.8 volts. We know the voltage in the 2, 3, 4, 5 combination. Since 2, 3, 4, 5 came from putting together resistors in parallel, the voltage has to be the same. So what's the voltage in R5? It's 10.8 volts. So I'm going to write that down. 10.8, because that's an actual, like, real physical thing. So what is the voltage in R234? Also 10.8 volts. We know the resistance of R234. It's 5.2 ohms. We know the voltage.
Wait, why is the voltage the same?
It's in parallel.
I thought the voltage was different in parallel.
Parallel, the voltage is the same. They're all identical. It's in series where the voltage is split up. All right. So if we know the resistance and we know the voltage, what can we find? Meditate on it. Now we find the current. I don't know where I'm going to do it. Current is equal to, that voltage divided by resistance, 10.8 divided by R234, which is 5.2, which gets me, I got 2.07. Okay. So, now that I know that that's 2.07, where did R234 come from? It was the combination of R4 and R23. How are they connected to each other? In series. What's the same in series? Current. Do we know the current? Yes. It's 2.07 amps. So that means that the current through 4 is 2.07, and the current through R23 is 2.07. We just figured out something about a real resistor, R4, which is that its current is 2.07 amps. Let's take a pause for just a second, because I can tell, I know where your brains are. Okay. Has any of the math I've done been difficult? No. This was the hardest thing maybe to wrap your brain around mathematically, right? Okay. All of it is division and addition, isn't it? Okay. The math in circuits is not hard. What's hard? Circuits, right? The organization of the information. I'm showing you probably a very inferior way that let me survive smoking pot in circuits class. Okay? Don't do drugs. There's other ways to organize this information. So come up with a way that works for you, right? Something, a way for you to keep track easily. Maybe it's colors, maybe it's numbers, maybe it's not, right? Maybe it's just working down the whole page in a line, right? Rather than having to go backwards on the page, whatever, right? But you need to be able to kind of clearly explain what's in series, what's in parallel, why you're doing what you're doing, all that kind of stuff. Okay, 2.07 amps. We know R4 is 2.07 amps. What do we now know about R23? It also has 2.07 amps. Do we know what R23's equivalent resistance is? 1.2 ohms. So what can we find? The voltage in 2.3 is current 2.07 times resistance 1.2 ohms, which gets me
2.5.
is it, yeah, 2.48
Yeah.
volts. Well, where did 2.3 come from?
2 and 3.
2 and 3 together. How were they added?
In parallel.
In parallel. What's the same in parallel? Voltage.
So they're both 2.4.
So 2 and 3 are 2.48 volts and 2.48 volts. We are now back to the beginning, aren't we? Which means we now know everything.
Plug stuff in.
Now, how do I find the voltage in resistor 1 if I know the current?
Just multiply them.
V equals IR, right? And if I want to find the current and I know the resistance and the voltage, what do? I do that, right? Basic math. So I did that. I got my whole table. I'm just going to fill this out. 4.23 divided by 1 is 4.23. We were looking for multiply. Sorry. Multiplication, division are the same thing. Let's see. Current in 2 is 1.24. This one's 0.83. Number 4 was 8.28. And then number 5, the current was 2.15. Okay, so there we go. How do I find the power for each individual resistor? Either current times voltage, which I know the current and the voltage for all of them, right? But even if I didn't, it would be I squared times R or V over R, depending on what I knew, right? Okay. So I'm just going to do current times voltage. This is 17.9 watts, 3.08, 2.06, 17.1, and 23. This does not look pretty, does it? Nah. No. It's colorful, but pretty, no. You're probably going to have to go back to the YouTube and watch this a few times to kind of get the flow and what's going on in this analysis. How do you check it? In the absence of a red or green box, and ChatGPT will probably hallucinate this circuit, okay? What do you do? Can we add all the voltages together and get 15 volts? I mean, energy must be conserved, right? If you add all those together, do you get 15? No, don't do that. The problem is like 2 and 3 were in parallel. They have the same voltage. You don't add them together. You would only count them once. But it becomes very difficult to have to trace that through. Same thing with the current. The current doesn't line up either. The total current through all these things is more than 4.23 amps. So don't ever look at your total voltage or your total current in a circuit and go, oh, I broke it. No, 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 no. However, there is one thing you can add up and compare. It's the power. Because energy must be conserved. Voltage might get replicated, current might get replicated, but the power will always work itself out. What's the total power? If we add up, let's do it this way. We know the total current in the circuit and the total voltage, 15 volts, right? So we can calculate the total power of this circuit by doing the current total times the voltage total. The current total was 4.23, and the battery was 15 volts. And when I did that, I got 63.4 watts. Okay? And if you add all of these powers together, you get 63.4 watts. You get a little bit of round off error there. I think I got 63.45 for one of them, and, right? But like power will work out because the power isn't shared. Power doesn't do series and parallel. Power is just how much energy was used up in a certain amount of time.
Where did you get the total current from again?
We found it. We found the equivalent resistance of the circuit, and so we found the equivalent current, which then allowed us to work backwards. Okay, let's talk reality for just a second. What am I going to ask you to do next Thursday on the exam when it comes to this? I expect you to be able to do series and parallel resistors, like be able to identify series and parallel. This question, which is one of the topics, I think it says DC circuit analysis or reduction or something like that. I am not going to make you do this full table. Would it take more than 10 minutes to work this through? Probably. Okay. What I am very likely to do is to ask, like, what is the current, like, right there? Like, I can just single out one resistor, right? And you can just stop once you find it, right? You don't have to do the whole circuit analysis. I could also, like, ask you to find the total current coming out of the battery, which means you've got to do all this, right? And then just stop at this point and not have to work your way back. I could ask you what the total power dissipated in the circuit is, in which case find the current and then just calculate the total power without having to go back. I guess what I'm communicating to you is in an exam situation, I wouldn't ask you to do this full analysis. Or if I did, it would be like 3 resistors, right? Okay? Because there just isn't time. But on your homework, things like that, practice this analysis so you make sure that you're learning your series and parallel rules and applying them correctly forwards and backwards through a circuit. It's a big ask, right? We've got 7 days, little less than 7 days, before you're going to get tested on it, plus all the other things that you've had to learn. So use the homework as a guide, right, for sort of the level of difficulty, and realize that I know you've only got 10 minutes to do a problem like this, and I've really tried my darndest to make sure that you, not me, you can do it in 10 minutes. Okay?
Could you do this one in 10 minutes? You?
Me?
Yeah.
Probably. Yeah, pretty close. I need you guys to leave right away. The Physics 2A students are coming in for their first exam.
Oh, okay.
Please try to assure them, smile at them, don't try to scare them, okay? But I need to get them going on their exam. I actually need to go to the restroom, so I need you guys to leave quickly.